Right now, at this very instant, two spacecraft built by human hands back in the 1970s are moving through territory that nothing from Earth had ever touched before. They're traveling at 35,000 miles an hour, and they're so far out that a radio signal moving at light speed needs nearly 24 hours just to reach one of them. Then, in April 2026, NASA engineers made a call that sent a chill through the entire space science community. They powered down one of the last instruments still running on Voyager 1. Not because it had failed, and not because the mission was wrapping up, but because Voyager 1's power supply is dwindling so fast, so silently, so unstoppably, that engineers were forced to choose between shutting the instrument off themselves or letting the whole spacecraft trip into an emergency shutdown on its own. That trade-off bought time for something NASA has nicknamed the Big Bang, a bold, high-stakes maneuver that could determine whether these two probes keep communicating with us into the 2030s or fall permanently silent within just a few years. But here's the part nobody's emphasizing enough. Even as all this unfolds, Voyager keeps turning up things out there that don't match our models. Things that are genuinely rewriting what scientists believed about the space between stars. The universe past our solar system isn't empty, isn't quiet, and isn't behaving the way anyone expected it to. This is the story of what Voyager has found, what it continues to find right now, and why its discoveries in interstellar space rank among the most unsettling and remarkable moments in the history of space exploration. To grasp why the Voyager story feels so remarkable in 2026, you need to rewind to how it all began. In September 1977. Two spacecraft lifted off within weeks of one another, not because NASA had set out to build an interstellar mission, but because the outer planets had lined up in a rare configuration that happens only once every 175 years. That alignment made it possible for a probe to use one planet's gravity to sling itself toward the next, touring Jupiter, Saturn, Uranus, and Neptune in one continuous run. The opportunity was there, and NASA seized it. Both probes were engineered for a mission lasting just 5 years. Expected to complete their planetary flybys, then coast silently into the void with dead transmitters and frozen instruments. Nobody truly anticipated what actually followed. Voyager 1 wrapped up its planetary work in 1980. Voyager 2 finished its own planetary tour in 1989, capped off by an iconic flyby of Neptune. Still, to this day, the only close-range look any spacecraft has taken at that faraway ice giant. From there, both probes turned outward, away from the sun and every planet science knew of, heading into darkness. And they simply kept going, year after year, decade after decade, with generation after generation of scientists gathering in the same control room at NASA's Jet Propulsion Laboratory in California, tuning into signals from machines that, by all rights, should have gone quiet ages ago. Voyager 1 now sits roughly 15.8 billion miles from Earth, while Voyager 2 is about 13 billion miles out. Numbers like that are so enormous they barely register with the human mind. So think of it this way instead. Sunlight takes about 8 minutes to reach Earth, but a signal from Voyager 1, traveling at that same speed, needs almost a full day. By November 15, 2026, Voyager 1 will hit the mark of exactly 1 light day from Earth, becoming the first object made by human hands to cross that line. That means a full day just for a signal to arrive, and another full day before any reply makes it back. If anything malfunctions on Voyager 1 at that range, NASA has to sit through a 48-hour wait simply to learn whether their fix worked. The sheer isolation and silence of that distance is hard to capture in words, yet the probes remain out there, still moving, still gathering data. And what they're gathering is reshaping everything we thought we knew. Let's begin with the power problem, since it's the countdown running underneath everything else. Both Voyager probes are powered by radioisotope thermoelectric generators, devices that convert heat released by decaying plutonium-238 into usable electricity. It's an elegant setup. No moving parts, no solar panels, nothing to burn as fuel. But plutonium-238 carries a half-life of about 88 years, and these generators have already been running since 1977. By April 2026, Voyager 1's generators were producing under half of their original launch output. That decline is steady, foreseeable, and impossible to stop. Roughly 4 watts lost every year. 4 watts might sound negligible, but when your entire spacecraft survives on barely more electricity than a dim light bulb needs, that annual loss is the line between continued science and total silence. To stretch out the mission despite this decline, NASA's engineers have essentially been running triage on a patient slowly bleeding out, switching off systems one after another to preserve the most essential functions. Heaters, cameras, scientific instruments, all have been powered down over the years to keep the mission alive longer. On April 17, 2026, engineers issued a command from California that took nearly 23 hours to reach Voyager 1. That command shut down the Low Energy Charged Particles Experiment, or LECP, an instrument that had operated almost without interruption since the 1977 launch, nearly 49 uninterrupted years. The LECP tracked ions, electrons, and cosmic rays out in interstellar space, charting invisible pressure fronts and shifts in particle density beyond the reach of our sun's influence. Losing it is a real blow to the science, but the alternative would have been far worse. Just weeks before that, in late February 2026, Voyager 1 suffered an unexpected power drop during what should have been a routine maneuver. The spacecraft came perilously close to triggering its automatic fault protection mode, a self-preserving shutdown that would have knocked out critical systems and forced a risky, multi-day recovery effort. Engineers switched off the LECP specifically to prevent that outcome, buying themselves crucial time, and that time is being spent preparing for the Big Bang. That's NASA's name for a complicated engineering maneuver never before attempted on a spacecraft this old, this remote, or this near the end of its power supply. The plan calls for switching off several power-hungry devices at once and swapping them for lower power substitutes. A careful rebalancing of the spacecraft's energy budget, aimed at freeing up just enough power to keep the science instruments running, possibly all the way into the 2030s. If the maneuver succeeds, engineers have suggested the LECP could even be reactivated. They've deliberately kept a small half-watt motor on the instrument running, just in case. The maneuver will first be trialed on Voyager 2, which has a slightly larger power cushion and sits closer to Earth, making it the safer test subject. Those trials are planned for May and June of 2026. If they go well, the same maneuver will be attempted on Voyager 1, no sooner than July 2026. Nothing about the result is certain. This is, after all, a 49-year-old spacecraft running software that can never be updated, hardware that can never be swapped out, and a power margin so razor-thin that a single unplanned roll maneuver nearly brought the mission to an end. Each command sent is essentially a gamble, and every response takes an entire day just to arrive. Still, NASA is pushing forward because what Voyager continues to uncover out there is simply too valuable to lose. So what exactly is it finding? What does interstellar space actually look like when measured firsthand, from within it, using instruments that have never before operated in that setting? The answer turns out to be strange, genuinely unsettling, in the best scientific sense, because the universe out there refuses to match the models built to predict it. Start with the boundary itself. For decades, researchers argued over where the heliosphere actually ended. The heliosphere is the vast bubble of particles and magnetic field generated by our sun, an invisible shield wrapping around every planet in the solar system. Astronomers initially guessed its edge might sit somewhere near Jupiter's orbit, then pushed that estimate farther and farther out. Voyager kept flying and kept not reaching it. Eventually, both probes did cross that boundary, called the Heliopause, with Voyager 1 crossing in 2012 and Voyager 2 following in 2018. What they recorded there defied every expectation. Take temperature first. As each craft passed through the Heliopause, they measured plasma at the outer edge, sitting between 30,000 and 50,000 Kelvin, scorching hot, far exceeding temperatures found within the sun's own magnetic reach. A thermal barrier that, intense at the solar system's edge, sits in a region so sparsely populated with particles that the heat can't actually harm anything, since there's almost nothing there to transfer it. Still, no model anticipated a plasma wall running that hot at the boundary. Nobody had predicted a 50,000 Kelvin barrier. Yet it's there, confirmed independently by both spacecraft. It's real, and its cause remains only partly understood. Then there's the cosmic ray puzzle. Within the heliosphere, the sun's magnetic field partially shields us, deflecting a good portion of the high-energy particles streaming in from across the galaxy. These cosmic rays, particles racing at nearly light speed, exist throughout interstellar space, though their presence is somewhat dampened inside our sun's protective bubble. When Voyager 1 crossed the Heliopause in 2012, its cosmic ray detectors recorded a sudden, near-instant spike in high-energy particle strikes as it left the sun's shielding behind. That spike itself wasn't a surprise. What did surprise researchers was just how intense the galactic cosmic ray environment turned out to be right outside the Heliopause. Voyager now sits in a region under constant bombardment from radiation, originating across the entire galaxy, particles that traveled millions of light years before colliding with a small machine from Earth. The spacecraft was built to withstand radiation and has endured nearly 50 years of exposure. Even so, the galactic cosmic ray levels in interstellar space turned out meaningfully higher than what scientists had projected using indirect readings taken from inside the solar bubble. The environment beyond the heliosphere is harsher, more energetic, and more hostile than the space we're accustomed to. Our sun has been quietly protecting us this entire time, and we only fully appreciated the scale of that protection once Voyager stepped past it and measured the difference directly. Second, density. When Voyager 2 crossed into true interstellar space, researchers were caught off guard to find plasma there running at roughly double the predicted temperature. The very local interstellar medium, the zone just beyond our solar bubble, turned out hotter and denser than any model had forecast. And it gets stranger still. As Voyager 1 has continued pushing deeper into interstellar space, the plasma density surrounding it hasn't held steady. It's been climbing. Year after year, as the craft drifts farther from the sun, the interstellar medium around it grows more crowded. Between 2013 and 2015 alone, electron density readings jumped 40-fold above the baseline recorded just past the Heliopause. 40 times denser, and not gradually, sharply. Voyager is heading deeper into a region that only gets more congested with particles the farther it travels. Scientists have offered two main explanations. One suggests interstellar particles slow down as they near the Heliopause, piling up like cars stuck at a bottleneck during rush hour, with Voyager now cutting straight through that traffic jam. The other proposes that the interstellar magnetic field, compressing against our solar bubble's edge, pushes charged particles away from the boundary and out toward the surrounding medium, leaving a thinner zone just outside the Heliopause and a denser one farther beyond it. Voyager may currently be entering that denser zone. Ongoing measurements should eventually reveal which theory holds up. But regardless, the steady, unpredicted rise in density is already pushing scientists to reconsider what they thought they understood about the space between stars. Third, and perhaps the most striking discovery, is the sound, or rather what serves as sound in a place no human ear could survive. In interstellar space, plasma, the ionized gas filling that void, can carry waves, pressure oscillations, much like the physics behind sound moving through air, only at far lower densities and frequencies. When Voyager 1's plasma wave subsystem, essentially a pair of 30-foot trailing antennas, picked up a steady, ongoing hum resonating through the interstellar medium, it immediately grabbed the scientific community's attention. Before this find, astronomers had only picked up brief, sharp whistling bursts in the Voyager data. Plasma wave spikes triggered by solar eruptions, sending shock waves outward through the Heliosphere. Those bursts had value, offering occasional glimpses into the interstellar medium's density whenever the sun produced an event strong enough to send ripples the full 14+ billion miles to Voyager. But they functioned like camera flashes, brief, bright, then gone. What researchers really needed was something continuous, and that's precisely what this hum provided. A steady, ongoing plasma wave emission resonating around 3 kilohertz, independent of solar activity, giving a constant window into the density of the space surrounding Voyager. Stella Acker, a Cornell University researcher on the team behind the discovery, compared it to a single, steady note held constantly, shifting only very slightly over time. Not random noise, not a glitch, but a genuine, ongoing vibration within the interstellar medium itself. For the first time, scientists could track the density of the space between stars continuously, rather than waiting for solar activity to cooperate. The discovery transformed how astronomers study the interstellar medium, the difference between judging a river by occasional raindrops and finally being able to dip a hand directly into it. Now, the other surviving instrument on Voyager 1, the magnetometer, is adding yet another layer to this picture. The interstellar magnetic field, faint but genuine, running through the space between stars, was measured by Voyager 2 at around 7 microgauss upon crossing the Heliopause. That's 64,000 times weaker than Earth's own magnetic field, yet it's undeniably present and stronger than astronomers had predicted. That unexpected strength, that extra push from the interstellar magnetic field, helps explain why the heliosphere hasn't behaved as expected across different phases of the sun's activity cycle. The sun cycles through roughly 11 years of rising and falling activity. During high activity stretches, with more solar wind streaming outward, scientists expected the heliosphere to swell, pushing its boundary farther out. During quieter stretches, it should contract inward. Yet when Voyager 1 crossed the Heliopause in 2012 and Voyager 2 in 2018, both during periods of elevated solar activity, astronomers expected a larger heliosphere than what they actually measured. Both probes recorded the boundary at nearly identical distances. The heliosphere had barely shifted. Researchers concluded the cause was the interstellar magnetic field pushing back harder than anticipated, effectively holding the bubble at a near constant size regardless of the sun's activity level. Our solar system's protective shell is being compressed from outside, with more force than anyone realized. All of this data comes from two machines that, in the words of former Voyager project manager John Cassani, were built not to fail, though never expected to last this long. As of 2026, Voyager 1 has just 2 functioning science instruments remaining: the plasma wave subsystem, tracking density shifts in the interstellar medium, and the magnetometer, tracking its magnetic field. Voyager 2 still has 3. Running on less than half their original power and communicating across distances so vast that a single command takes a full day to arrive, these few remaining instruments represent the only direct contact humanity has ever had with the interstellar medium. Every other piece of knowledge we have about that space comes from indirect measurements, gathered by telescopes peering outward from inside our solar bubble. Only Voyager is actually stationed there. Only Voyager is directly touching it. And what it's touching is hotter, denser, and louder than any model predicted. There's now a new spacecraft launched in 2025 called the Interstellar Mapping and Acceleration Probe, or IMAP. Scientists describe it as Voyager's findings taken to an entirely new level of precision, capturing the heliosphere's boundary with far sharper resolution than anything measured before. IMAP orbits a stable point roughly 1 million miles closer to the Sun than Earth, building comprehensive maps of how the heliosphere interacts with the surrounding interstellar medium. Combined with Voyager's ongoing transmissions, its data is producing the most detailed picture ever assembled of the bubble enclosing our solar system, and every fresh image from that picture raises new questions. The heliosphere isn't the smooth, spherical shape once shown in textbooks. It's lopsided, molded by the direction of the interstellar magnetic field pressing against it, stretched long on one side and squeezed flat on the other. Our sun itself is moving through the interstellar medium at roughly 56,000 miles per hour, cutting through a region that's actively resisting it. Voyager rides in the wake of that motion, measuring the disturbed environment left behind, as our solar system carves its path through the galaxy. Whenever the Big Bang maneuver actually happens, it will decide how much more of this uncharted territory Voyager gets to explore before the silence sets in. Engineers remain hopeful. The same people who built these probes for a 5-year mission and then watched them keep running for nearly 5 decades aren't the type to give up easily. If the Big Bang succeeds on Voyager 2 this summer, followed by success on Voyager 1 later in 2026, there's a genuine chance both probes could keep sending back science data well into the 2030s. If it doesn't work, the mission could end within just a few years. Either way, the clock keeps ticking. Out there, the universe, hotter, denser, and louder than predicted, isn't going to pause and wait for our understanding to catch up. What makes Voyager's current situation in 2026 especially remarkable is that its most critical discoveries are coming from the weakest, most stripped-down version of the mission that has ever existed. At launch, each probe carried 10 instruments: cameras, spectrometers, particle detectors, magnetometers, plasma analyzers, the complete toolkit needed to explore a totally unfamiliar environment. As the decades wore on and power kept declining, instruments were shut down one after another. Cameras went first, since there was nothing visible to photograph in the featureless dark of interstellar space. The ultraviolet spectrometer followed, then others. Each shutdown marked a quiet farewell to another piece of scientific capability. And yet, remarkably, the instruments that survived, the ones measuring plasma waves and magnetic fields, the ones directly sampling the character and behavior of the interstellar medium, happened to be exactly the tools best suited to the questions Voyager is now uniquely positioned to answer. It's almost as though the mission somehow anticipated which tools it would need at the very end, kept them alive, and is now deploying them at precisely the right moment to answer questions that didn't even exist back when the probes first launched. The hum within the interstellar medium, the climbing density of the space between stars, the scorching plasma wall at our solar system's edge, the uneven and turbulent shape of the Heliopause, none of these were discoveries anyone foresaw in 1977. They're gifts from the universe itself, delivered by 2 machines that refused to die, in a place they were never designed to reach. Consider, too, what it means that the Heliopause itself turned out to be far from uniform. When Voyager 1 crossed it in 2012 and Voyager 2 followed 6 years later in 2018, the 2 probes were headed in completely different directions, aimed at entirely different regions of the sky. They're now so far apart that each is actually farther from the other than either is from Earth. And yet, despite that, their 2 boundary crossings looked strikingly different from one another. Voyager. One recorded dramatic magnetic field fluctuations right at the moment of crossing. Voyager 2 saw none of that same turbulence, but instead detected a thin layer of hot plasma just outside the boundary, a cosmic ray boundary layer that Voyager 1 had missed entirely. The Heliopause, it turns out, isn't a clean, smooth, uniform shell at all. It's a messy, turbulent, asymmetric boundary that behaves differently depending on where and when it's crossed. Our solar system isn't floating inside some perfectly symmetrical bubble. It sits within a structure actively pushed, shaped, and squeezed by the interstellar environment, surrounding it from every direction, and unevenly so. The orientation of the interstellar magnetic field, the local density of the medium, and the motion of our solar system through the galaxy all press against the heliosphere from different angles and with different intensities. Voyager 1 and Voyager 2 delivered just 2 data points along that boundary, 2 readings taken years apart at 2 separate locations. And even from those 2 alone, the picture that emerged proved far more complicated than any model had anticipated. Imagine, then, how much remains unknown about the other 2/3 of that boundary that no spacecraft has ever measured. Here's what strikes me most about all of this. We find ourselves in the extraordinary position of having two machines, launched before personal computers existed, before the internet existed, before most people watching this were even born, that are right now in 2026, touching territory no other human creation has ever reached. They're measuring a region where our best scientific models turned out wrong in several major ways. The Heliosphere isn't the size we assumed. Its boundary isn't the temperature we predicted. The interstellar magnetic field isn't as weak as we thought. The density of the medium beyond our solar system keeps rising in ways our theories still struggle to explain. And running beneath it all, steady and unbroken, is a hum, a genuine, measurable, continuous vibration of plasma between the stars, carrying information about a universe we're only just learning how to interpret. Every single day these two probes keep functioning adds another day of data from a place no currently planned mission will reach again for decades. Even if a dedicated interstellar probe were funded and launched today, it would take at least 15 years just to reach where Voyager 1 currently sits, and considerably longer still to push beyond it. For now, Voyager remains our only voice from the space between the stars, and that voice keeps telling us things that are genuinely reshaping our understanding of where we live and what surrounds us in every direction across hundreds of trillions of miles. The universe beyond our sun isn't empty, it isn't silent, and it isn't what we assumed it was. Subscribe now so you never miss what the universe reveals next. Share this video if these discoveries deserve more attention than they're currently getting, and drop your questions below, because Voyager's story, even at 49 years old and 16 billion miles from home, is far from finished.